Chapter 16, Current of Electricity, Part 3. In this Part 3, we will be zooming into what is resistance. Okay, so these are the learning outcomes. Okay, so what exactly is resistance? In layman terms, electrical resistance means the slowing down of the flow of electrons or charges in a circuit. Whenever electrons flow through a component, they will have a lot of collisions with the atoms and ions inside it. And this collision actually slows down the flow of the charges. Okay, the degree of the opposing force in which an electric current experiences when it flows through a component is known as the resistance of the component. So another way of thinking it, or in simplified manner, it simply means it's a measure of how difficult it is for an electric current to pass through a material. It is the property of the material. Okay, so when we have something with high resistance, we say that the current is very low. Okay, because it means that there is a lot of restriction, a lot of resistance, okay, a lot of blockage, a lot of collision, a lot of blockage, and then the rate of flow of charges will be slower, and therefore there is a decrease in current. Okay, so whenever there is high resistance, okay, it's like a lot of friction is generated, so a lot of energy is being converted into heat and light. Okay, so but then in physics terms, you need to know the definition of resistance. Is not like how much blockage force, but we define it as the ratio of the potential difference V across the component to the current I flowing through it. Okay, so there's a formula for it, and this definition comes exactly from the formula. It's just like mass V divided by I, ratio of potential difference to the current I flowing through it. Okay, so it's like very VIR, very important. Whoever starts with R, or very intelligent R. Okay, so VIR, that's the formula for resistance. Okay, so V is the potential difference, I is the current, and R is the resistance. Okay, SI unit for resistance is ohms. Okay, so we look at what examples. A lamp draws a current of 0.25 ampere when it's connected to 240 volt source. What is the resistance of the lamp? So I'm looking for R. So it's V divided by I, which is 240 divided by 0.25, which is 960 ohms. Next one, calculate the current flowing through a 5 ohm resistor when a potential difference of 2 volts is applied across it. So in this case, I'm looking for I. So I is V over R. So it's 2 volts divided by 5 ohms. I get 0.4 ampere. Okay, so what are some of the components or things in a circuit that gives rise to resistance? Okay, we have something called resistors. We have fixed resistors and variable resistors. So fixed resistors looks like this, and variable resistor looks like this. Okay, so for fixed resistor, the resistance cannot be changed. Okay, the symbol for a fixed resistor is just a long box, rectangle box. Okay, and then for variable resistor, or we call it a rheostat, it means that I can vary the amount of resistance. So when I vary the amount of resistance, I can control the current in the circuit. So I can vary the amount of current in the circuit. So it's often used for volume controls, brightness control for light, things that when I turn, I can become brighter or softer. I can adjust the fan speed, even like how much current that flows through it. Okay, so the symbol is still a rectangle, but in this case with an arrow up. So this is the electrical symbol for variable resistor. Okay, so how does a variable resistor works? Okay, so in a variable resistor, there is many resistance wire over here, and there is a slider over here. So by sliding the contact, I get different, my current will flow through different length of this resistance wire, and I get different resistance. Okay, so how does it work? It looks like this. Okay, I will play the video over here. Okay, so I'm going to pause over here. So the current flows in from one end is connected at the bottom and the other end is connected at the top. So the current flows in from here, it flows through all this resistance wire and then all the way up to reach this sliding contact, and then you go up. Okay, this part where there is very little resistance all the way out to the circuit. So by adjusting this slider, I get different length of the resistance wire. Okay. Okay, so to get the lowest current means the highest amount of resistance, I need to shift this sliding contact all the way to the right. Okay, so if I shift it all the way to the right, means that the current need to flow through the entire length of this resistance wire before I go up to the sliding contact and out. So this is the highest amount of resistance, the current will be the lowest. Okay, so you can take a look at here. So variable resistance is usually connected in series to a circuit. So I have one end that goes in, okay, from the top, and the other end that goes in from the bottom. Okay, one end going from the top, one end going from the bottom. Okay, so the current is going in here. Okay, so when I shift it to here, you will see that I have very little resistance. So my current flows in here, it go up to the sliding contact, go through this metal bar and out. So when I have very, very little resistance, my current will be very high as compared to when my resistor is over here. Okay, this is when I have maximum resistance. So the current flow in here will flow through all these black wires all the way to up this sliding contact and out here. So this at the highest resistance, the current is the lowest. Okay, the current increases. This resistance is very little. Okay, let's move on. Okay, so how do we measure resistance of certain components? Again, you can use a multimeter, but you are not allowed to use a multimeter for O level. So you need to know how do we measure resistance. In order to measure resistance, we need the voltage and the current. So for example, to measure the resistance of the light bulb, I need the voltage across the light bulb as well as the current flowing through it. So recap again, to measure the voltage across the light bulb, I need a potential difference across the light bulb. I need to connect the voltmeter in parallel to the light bulb, and then the current will be, I just will use my ammeter in series to the light bulb. Okay, so you can pause here and look at the questions. I'm going to go through now. There is a 3-volt source connected to a light bulb. The ammeter reads a reading of 0.2. What is the reading on the voltmeter? Okay, so you must know that the battery gives you 3 volts. 3 volts is only used up by the light bulb. There is no other component in the circuit that uses energy except the light bulb. So the entire 3 volts will be used up by the light bulb. So the potential difference across the light bulb will be also 3 volts. Okay, the energy given by the battery, to each charge must be used up in the circuit. Okay, so the voltmeter reading will be 3 volts. What is the resistance of the light bulb? Okay, so resistance of light bulb R equals to V over I. So I will have 3 volts divided by the I, which is 0.2 ampere. Okay, and then next, the switch, so it's over here, voltmeter reading will be 3 volts, and then R will be 15 ohms. Okay, then go back to here. So the circuit is switched on for 5 minutes. Determine the amount of charge. So remember, charge, there's a formula for it. Usually charge is the formula linked to current. So Q equals to I times T. So the current is 0.2 times 5 minutes changed to seconds. And then the energy is always using the formula for volts, or volt done, energy is the same as work done. So I'm looking for the W is V times Q. Okay, so the V is actually 3 volts times the amount of charge, which we have calculated in part 1. So the amount of charge is actually 60 coulombs. And then I just use V times Q, which is 60 coulombs times the 3 volts. Okay, I get 180 joules. Okay, so how do we determine the resistance of an unknown resistor? Okay, you need to memorize this set of experiment because you will be asked to describe experiments to determine the resistance of certain components. So in this case, we have a setup like this. I want to measure the resistance of this resistor. So I put my potential, my voltmeter across this resistor to measure the potential difference across this resistor, ammeter connected in series. And the purpose of this rheostat is to vary the current, because you know that whenever we are doing experiments, we don't just take one set of V, one set of I, and then we take V divided by I. Okay, we usually do multiple sets of V, multiple sets of I, and then we plot a graph. So in order to get multiple sets of V and multiple sets of I, we need to use a rheostat to vary the current. So I get different values of I and V. Okay, so you can read. The first step, you adjust the rheostat to maximum resistance so that the starting current is small. We don't want a huge current to flow at the start because that will generate a lot of heat. So we want minimum heating because heating do affect the resistance of the resistor. Okay, then after that, I record ammeter reading, voltmeter reading, and then adjust the rheostat again to get another set of ammeter reading, voltmeter reading, and then repeat to get more sets and plot a graph of V against I. The gradient at this point will just be, or any point V, you take the V here divided by the I here, you get the resistance of the thing. Okay, so this is a picture that shows you what exactly is resistance. So the volts is the battery. Okay, the battery provides pushing energy for the charge. This green guy over here is the ampere, is the charge that moves. How fast this charge moves gives you the current. And the ohm, which is the resistor, is the one that is tying the rope, preventing it from moving. Okay, so the higher the resistance, the slower this green guy moves. Okay, the lesser the ampere. Okay, next, we also have a formula to determine the resistance of components. Okay, so the resistance of an object actually depends on its shapes and its material. Okay, so you may scan the following QR codes to play with a simulation. Okay, and then the simulation looks like this. You can play the simulation. You can vary the resistivity. We'll talk about what is resistivity, but you can vary this term called resistivity. You can vary the length, and you can vary the area, and you look at how the resistance of it changes. Okay, I'm going to share with you how does it looks like. Okay, so if you scan the QR code, you will be able to see this. So you can see as I increase the resistivity, my resistance increase. Okay, and as my resistance decreases. Okay, then if I increase my length, longer and longer and longer and longer, the resistance also increase, vice versa. Okay, but for the cross-sectional area of the component, as I increase the area, the resistance actually gets smaller. As I decrease the area, the resistance actually increase. Okay. Okay, so there is actually a formula for it. Okay, but before I introduce the formula, you must know that the resistance, okay, is directly proportionate to the length and inversely proportionate to the area. So what happens is if I have a longer length, it's like I can think of my object as a tunnel. Okay, if the longer the tunnel is, the longer time I take to crawl through. So the person crawling through is the charges moving through it. So if I have a long tunnel and a short tunnel, obviously, in a short tunnel, I will come out of the tunnel faster. So my current will be higher, I have lesser resistance. While for a long tunnel, I'll take a long time to crawl through it, okay, because there's more collision or it's very difficult to crawl through a long tunnel. So the current will be reduced. It has a higher resistance. Okay, but for cross-sectional area, if I have a fat tunnel and a thin tunnel, obviously it's easier to pass through a fat tunnel. Okay, in a fat tunnel, there's lesser collision because the particles are more spread out. Okay, so there is lesser collision. So the charges can flow through it more easily. I will have a higher current, lower resistance. But if the tunnel is very thin, then the cross-sectional area is very small, then it's very hard for me to squeeze through it. There'll be a lot of collision, and therefore the rate of flow of charges will be very slow, and current will be very low, and it's said to have a very high resistance. Okay, so there is a formula that relates to it, which is R equals to rho L over A. Rho is the resistivity of a substance. Okay, this resistivity is a measure of the amount of resistance that the material provides. Okay, it's a property of the material and we cannot change it. Different materials have different amount of resistance, which is given by this resistivity, and then followed by the length of the object and the area, cross-sectional area of the object. Okay, so resistivity is the resistance of material for a unit area per unit length. The unit for resistivity is ohm meter. Okay, this rho is ohm meter. Okay, how much resistance per meter? Okay, so you can take a look at this table. You don't need to memorize. Things with very low resistivity are usually very good conductors, very little resistance. So we have silver is the best, followed by copper. Okay, and then materials with very high resistivity are insulators. They are poor conductors. So what happens is they have a lot of resistance. So when charges flow through it, it generates a lot of heat and is often used in your heating element like nitro. Okay. Okay, so let's come and look at a few examples. Okay, so you have a conductor has a length L of 4 cm and a cross-sectional area of 2 cm squared. Given that the resistance is 5 ohms, okay, this wire over here has 5 ohms. What is the resistance of each of the following? Okay, I like to do by ratio. So I do one by one. I vary either the length or the area first. So I compare. So this wire over here has a resistance of 5 ohms. I compare this wire to part A. Part A, my area is the same, but my length double. So when I have a longer wire, it's harder for me to pass through it. So resistance is higher. So you can see that the length doubled from 4 cm to 8 cm. So as the length doubled, the resistance will also double. So it will be 5 ohms here and 5 times 2, which is 10 ohms over here because the length doubled. Okay, next one, part B. Okay, now I have the same length as this. Okay, or I go back to my original question. This is 5 ohms. Okay, now both my area and my length increase. Okay, I know that as I increase my length, doubled, my resistance doubled, becomes 10 ohms. But my area is bigger, my cross-sectional area is bigger. It's easier for the charges to flow through it. The resistance drops, and it drops by 2 times again. So I initially, because of this length, 8 cm, I'm 10 ohms, but now I decrease by half because of the bigger cross-sectional area. So my resistance dropped by half, so I'm back to, I am actually back to 5 ohms. Oh, I'm sorry, this answer is wrong. Okay, it should be 5 ohms. Okay, then for part C, okay, I have the same length, but I increase the cross-sectional area. So I double the cross-sectional area. It will be easier to flow through. The resistance will be lower. So the resistance, instead of 5 ohm, it will become 2.5 ohms. Oh, I swapped the wrong order. This should be 2.5 ohms. Okay, not 5 ohms. And then Next one, I increase the length and decrease the area. So I will double and then double again. So I will get 20 ohms. Okay, next question. You can take a look at this. A length of resistance wire 50 cm long is connected in series with an ammeter and a 3-volt battery. The ammeter reading is 0.15 ampere. Okay, so they want to ask, determine the resistance of the wire. So the resistance R is V over I. So you get 3 volts divided by 0.15 ampere. You will get 20 ohms. So the resistance of this wire is 20 ohms. Okay, next question. So now I double the length. So I will have doubled the resistance. So instead of 15, I become 30 ohms. But this cross-sectional area is again half. So I'm thinner now. My resistance will again double. Okay, so now my resistance is actually 15 times 2 times 2, which is 60 ohms now. Okay, my resistance of this wire has become 60 ohms. Okay, so 20 times 2, or sorry, 80, 20 ohms, then times 2 is 40 ohms, times 2, 80 ohms. Okay, 80 ohms over here. So now what is my new current? Okay, new resistance is 80 ohms, and the ammeter reading is no longer 0.15. So now I'm interested in I is V over R, so it's 3 volts divided by 80. I will get 0.0375 ampere. And then the last question, it says that given that the diameter of the 50 cm wire, okay, so this is 50 cm is 5 mm, determine its resistivity. So I'm going to substitute into the formula. Resistivity equals to resistance times area over length. So resistance is 20 ohms. I use the original one times the cross-sectional area of the original one, pi r square. This is r square. Okay, so I take the diameter divided by 2 and then square, I change it to meter, divide by 50 cm, which is 0.5 meter. I remember you need to change everything to SI units, which is meter. And for cross-sectional area is pi r square. So it's pi times d over 2 square. Okay, so you get this ohm meter. Okay, that's it.